So yeah, good morning, everyone. Today I'm happy to present to you Sung-Chul Yoon, who is going to give our colloquium. And Sung-Chul is definitely one of the people in the field who have inspired me a lot throughout my career. So Sung-Chul made his PhD in Utrecht in Netherlands. And then he got this nice fellowship, the SNe Fellowship in the Netherlands, that he took to Amsterdam. Then he moved to actually UCSC as a postdoc in Lick Observatory. And after that, back to Europe to Bonn as a staff scientist. And since a few years back now, Sung-Chul is a professor at the Seoul National University in Korea. So with that, I would like to welcome Sung-Chul and ask you to share your screen so that you can start your presentation and you feel comfortable. Thank you so much.
Okay, thank you. Okay. So can you see the screen now? Yeah, yes. Okay, great. Yeah. Okay, yes, let me start. Yeah. Just trying to, okay. Okay, so thank you for the invitation. It's really, I'm very glad to give a talk here. Actually, it's been more than 1 year that I couldn't travel to international conferences, and that means that I haven't given a talk, especially in English, for more than a year. So it's really long time to give a scientific talk like this. But anyway, I'm very happy to have this chance. So I'd like to talk about progenitor stars of type 1b and type 1c supernovae. And so especially about the model predictions and how to constrain the models from pre-supernova searches and supernova-like curves. As a reminder, there are different types of supernova. Type 1 usually means that you don't see any hydrogen lines in the spectrum. And type 2 means that you see hydrogen lines. And for type 1 supernova, there are 3 different types. One is type 1a, which one is, this one is famous thermonuclear explosion of white dwarf. And the other one is type 1b. That means that you see helium lines, but there's no hydrogen lines. And there is a type 1c, means that no hydrogen and no strong silicon lines. And there are also different types of type 2 supernovae. And all of these, except type 1a, originate from massive stars. So they are produced by core collapse. And the light curve of type 1bc supernovae looks like this. It's very different from usual type 2p supernova light curves. For type 2p supernova, you see there is a long durated plateau phase here. That's mostly because of hydrogen envelope. So when the supernova explodes, hydrogen recombination makes the photosphere, and the plateau phase lasts when the photosphere recedes into the helium core until the photosphere recedes into the helium core. So that means that for most type 2p supernova, the power source is the thermal energy release due to recombination of hydrogen. But for type 1 supernova, the supernova light becomes bright because of radioactive decay in nickel. So it's very different from usual type 2 supernova. And the spectra look like this. So this is the typical type 1, sorry. This is typical type 2 supernova spectra. You see there is a strong p signal profile of H alpha here. And but for type 1b and 1c supernova, you don't see any hydrogen line here. For 1b, you see several different helium-1 lines. And for 1c supernova, there is no helium line, and there's a kind of weak silicon line here. Sometimes this silicon line is very broad, and such type 1c supernova is called broad-lined type 1c supernovae. And you know that there is a very nice correlation between the peak magnitude and the decline rate of supernova like curves in type 1a supernova, which is the thermonuclear explosions of white dwarf. So this is the peak B magnitude, and this is the so-called delta M15B. That means that the magnitude difference between the peak and the 15 days later after the peak in the B band. And for type 1a, for ordinary type 1a supernovae, there's a clear correlation like this. And that's why we can use type 1a as a distance indicator. But for type 1bc supernova, you don't see such a correlation. So it's quite irregular. So it's very different. And we know that type 1b and 1c supernovae, they originate from massive stars, mostly because they occur in star-forming galaxies. And they preferentially occur in a light concentrated region. So for example, this is the work by Kelly et al. In about 10 years ago. And this x-axis shows you the fractional flux in G band in a host galaxy. And different lines gives you a cumulative distribution of the supernova site in a host galaxy. And as you can see here, type 1c supernovae, they are quite concentrated in bright region in a host galaxy compared to type 1 or type 2p supernova. Type 1b supernovae also are more concentrated in light in bright region compared to type 1a or type 2 supernova. So this means that type 1b and type 1c supernovae, they originate from relatively more massive stars compared to usual type 2 supernovae. So we believe that they originate from relatively massive stars. And the reason why I am interested in type 1b and 1c supernovae is because the progenitors would not have any hydrogen envelope. And that means that they have lost their hydrogen envelope during the evolution. That can give us very important clue about the massive star evolution. So it is very well known that massive star evolution is primarily determined by mass loss history. Low mass stars, they do not lose much mass, but high mass stars, the surface luminosity is fairly close to the Eddington limit. So the surface layers are not very well bound by gravity. And the mass loss rate is proportional to the luminosity to the power of 1.5 usually for the main sequence stars. And that means that the mass loss rate is very sensitive to the mass. So to the power of about 4.5. So that means that if a star is born with a higher mass, they would lose more mass. And the evolutionary history can be very different because of this kind of mass loss history. And this mass loss rate also depends on metallicity to the power of 0.7. So metallicity effect would be also very important in this case. So for type 1b and type 1c supernovae, they must have experienced a lot of mass loss. And they are very good test case for this kind of mass loss history of massive stars. Massive star evolution of single stars, the standard scenario tells us that the evolution of massive star would sensitively depend on the initial mass. For example, if the initial mass is less than about 40 solar masses, then they would evolve to red supergiant star after the main sequence. And if the initial mass is less than 25 solar mass, then they would end up as red supergiant when they die, and they would explode as type 2P supernova, usually. And if the initial mass is between 25 and 30 solar masses, then they would lose a large fraction of hydrogen envelope, but they still would keep some tiny amount of hydrogen envelope, and they would explode as type 2L or type 2B supernovae. And if the initial mass is even higher, between 30 and 40, then the entire hydrogen envelope will be lost during the red supergiant phase, and the star will become Wolf-Rayet star. That means the naked helium star, and they would end up as type 1b or 1c supernovae. And if the initial mass is even higher than 40 solar masses, then they would not undergo red supergiant phase, but they would become blue supergiant because of strong mass loss. And they would become Wolf-Rayet star after this phase, and they will explode as type 1b or 1c supernovae. The one problem with this scenario is that, if we compare the model prediction, especially the final message of massive stars from single stars, compared to the ejecta message of type 1b and 1c supernovae, usually stellar evolution models predict too high mass at the end of at the final stage. For example, this is the final mass and as a function of the initial mass. So this is the stellar evolution model prediction. And this black line is the most recent evolutionary model prediction. So as you can see here, these are predicted 1b and 1c supernova progenitors, and the predicted final mass is higher than 10 solar masses. But we can infer the ejecta message of type 1bc supernovae from the supernova light curves. So the idea is that if the ejecta mass is very high, then the diffusion time of photon is very long. So the duration of the supernova light, becomes longer for higher masses. So from that property, we can infer, roughly infer the ejecta message. And here is an example by Lyman et al. And there are many other studies like this. And typically, it looks like that the ejecta message of type 1b and 1c supernovae lies between 1 to about 4 solar masses. So usually centered at around 3 or 2 solar masses. So that means that the final message of 1bc supernova progenitors must be between about 2 to about 5 or 6 solar masses, much lower than stellar evolution model prediction. So that's why many people think about binary star evolution instead. One good thing with the binary star is that you can remove hydrogen envelope even without any strong stellar wind, just by binary interactions. So here's an example here. For example, 2 stars may orbit around each other in a binary system. And this star would evolve into red supergiant. But since the red supergiant envelope should be enclosed in the Roche-Loeb radius, there must be mass transfer to the secondary star. And then this star will lose hydrogen envelope, and the primary star will become naked helium star. And in this case, if this star explodes, then it will become type 1b or type 1c supernovae. So, as I said, this naked helium star does not need to be massive. For example, this helium star mass can be as low as 2 solar masses, for example. And it can explain very well the observed ejecta message of type 1bc supernovae. So that's one of the reasons that we believe that the most of type 1b or type 1c supernovae originate from binary systems. And evolution of the mass donor would look like this, for example. This is the so-called Kipnan diagram. This x-axis gives you the evolutionary time until core collapse in terms of, until core collapse in log scale. And y-axis gives you the mass coordinate. And here is the surface of the star. So in this case, the initial mass was 16 solar masses. And it had a 5-day orbit with a companion of 14 solar mass star. And this star has lost this amount of hydrogen envelope by mass transfer in binary system after the main sequence. So this is the helium burning stage. And this is at the end of helium burning stage. You can see my pointer. You can see my, okay.
Yes.
Yeah. And here is a helium burning stage. So at the end of the main sequence, the entire hydrogen envelope has been lost. So the remaining mass is about 4 solar masses here. So 4 solar masses helium star can be produced like this. And this is the evolution of binary system on the HR diagram. So these field circles gives you the starting point. And blue line is the evolution of the primary star, mass donor. So here is the main sequence phase. Then right after the main sequence, mass transfer starts. And star becomes very faint as a result of mass transfer because the star becomes thermally unstable. And here is the end of mass transfer phase. Then star contracts to find thermal equilibrium state. And then helium main sequence starts somewhere here. And here is the end of helium burning phase. Then after the helium core burning phase, the star helium envelope expands again. Then this star will explode at this point when the surface temperature is a few times, well, maybe about 20,000 Kelvin. So this is one example. So in this way, we can make binary star models and make some predictions about progenitors. So we can make both single stars and binary stars. And the question is that how to constrain model predictions on supernova progenitors. The best way would be direct searches for the progenitors in pre-supernova images, because that would give us very strong constraints about the surface properties. For example, the radius, surface temperature, and total luminosity and so on. But as I will tell you later, it's not easy for type 1b and 1c supernovae. There are many identified progenitors of type 2 supernovae, but there is only a few candidates for type 1b/c supernovae. And the other way is to use the information of supernova spectra and light curves. From this, we can infer the ejecta mass, and also we can infer chemical composition in the progenitor, for example, whether it's a helium rich or not, helium poor, and so on. So I will tell you about this later. Another way would be look at the host galaxy properties. For example, how the stellar population age would be around the supernova site, and how the supernova type changes as a function of metallicity and so on. But this is very interesting topic, but I would not tell about this here. So I will focus about the first two topics. So the first question I'd like to discuss here is that what can we learn from pre-supernova searches? So 1BC progenitors, they lost hydrogen envelope basically. That means that they are very compact compared to type 2 supernova progenitors. So if a star has a hydrogen-rich envelope, then during the final stage, usually the hydrogen-rich envelope expands quite a lot. So usually they have radius of several hundred solar radii. Sometimes it's a blue supergiant like 87A supernova progenitor, but even in that case, the radius can be as large as 50 solar radius. But typically, it's larger than 100 solar radii, and the surface temperature is about 4,000 Kelvin up to about 10,000 Kelvin. So usually it's a red supergiant star, red supergiant or yellow supergiant star. But 1B progenitors, they have lost entirely hydrogen envelope. And that means that the progenitor star is much more compact than hydrogen-rich progenitors. So as a result of that, the radius at the final stage is much smaller than this case. Usually it's about a few times solar radii. Sometimes the helium envelope can expand quite a lot. Then it can have as large as 100 solar radii sometimes. But usually it may be about several times solar radius. So the surface temperature would be larger than about 10,000 Kelvin and typically less than about 50,000 Kelvin at the very final stage. Type 1C progenitors would be even more compact because, well, I'll discuss about this later, but they are supposed to have lost helium envelope mostly. So in this case, given that they are just metal stars, the radius would be less than about 0.5 solar radius, and the surface temperature would be higher than about 100,000 Kelvin. And this means that optical brightness would be most high. The optical brightness becomes higher from the right to the left. So type 2 progenitors are usually very bright in the optical, but 1B progenitors would be much less bright, and 1C progenitors would be even less bright. And that's why it would be very difficult to find out, to identify type 1B or 1C progenitors. So we have 3 candidates so far. One is IPTF 13BVN. This one was type 1B supernova. And then progenitor was identified here by these people. This progenitor was fairly bright. And I'll tell you later about this, but it doesn't look ordinary to me, but anyway, marginally okay. And there was another candidate reported by Van Dijk in 2018 for supernova type 1C to 2017 EIN. There was a progenitor candidate here. And there was another candidate recently reported. That one is supernova 2019 YVR. This one was type 1B supernovae. But as I will tell you later, these two are extreme. I mean, they are outliers. They don't look like ordinary type 1BC supernovae. So, so here is the model prediction about the volumetric luminosity of type 1BC supernova progenitors. It's a function of mass. So here, when you see here is the y-axis is the mass, final mass of type 1B or 1C progenitors at the very final stage. And x-axis is the luminosity, volumetric luminosity. And here, the open symbols gives you the mass luminosity relation for ordinary ultra-rare stars in our galaxy. And as you can see here, for a given mass, the final luminosity of the progenitor is much brighter than ordinary. Ordinary means that helium burning stage, helium stars. That's because during the final stage, the stars undergo very different shell burning stages, and the volumetric luminosity becomes much higher. So you should be very careful when you compare the progenitor stars with galactic Wolf-Rayet stars, because the property of progenitor stars during the helium burning phase and the final stage would be very different in terms of luminosity and temperature. So, so this figure shows you that the progenitor stars would be much brighter during the final stage in terms of volumetric luminosity. And this is the HR diagram of the model prediction compared to the galactic Wolf-Rayet stars. So these open symbols gives you the luminosity and temperature relation for galactic Wolf-Rayet stars. And these colored symbols gives you the examples of some type 1b and 1c supernova progenitor models at the very final stage.
Sung-Chul, can I ask you? Oh, it looks like you're gonna say it. Never mind.
Okay. So these are helium-poor models. So because they do not have much helium at the envelope, they are very hot. And these are helium-rich models. So these are supposed to be 1b progenitors, and these are supposed to be 1c progenitors. So these progenitors would have very different surface temperatures.
Right. So is it going back to the previous slide?
Yes.
Is it just radiatively driven winds that are the difference between the 1Bs and the 1Cs? So the hydrogen is all binary,
Yes.
you know, effects, but it's the differentiation between 1Bs and 1Cs that's basically mass or luminosity driving away the helium?
Yes, that would be the case. Yes.
Okay.
That's we still do not fully understand the wind from helium stars. So I personally still do not know how to remove helium envelope from the progenitor star. But these models have been made just sort of, these models I made from my new mass loss wind prescription. But still I have some difficulty in making 1C progenitors. I will discuss about that later.
Okay, yeah, that's very interesting.
The idea is that the helium envelope would be removed by stellar wind. That would be, yeah, most important way, yes.
Okay, so I have a question, but also Andy has a question. So first, my question, your HR diagram you showed previously, the star entered the case BB mass transfer, and also we could see that a little bit in the Kippenhahn diagram. Is that not then important for removing the helium envelope?
For some cases, yes, but not mostly. Yeah, so some tiny fraction of binary systems would undergo very strong case BB mass transfer, but most of them would not. Yeah.
Good. And Andy has a question in the chat, and it is the luminosity dependent on metallicity in addition to driving the mass loss?
Luminosity, is the luminosity dependent on metallicity? Luminosity does not strongly depend on metallicity usually. Luminosity depends on mass mostly. So metallicity dependence of luminosity is very weak.
Okay, great.
Okay. Mass loss itself would depend on metallicity. Yes, of course. Yes. Mass loss would become stronger for higher metallicity. Yeah. But in any case, these are compact stars, but one interesting effect can be made by stellar winds, because these stars are also supposed to have strong winds usually. For example, Wolf-Rayet stars, they usually have a very high mass loss rate. So what can happen here is that so progenitor star can have very compact structure, but if the progenitor has fairly strong wind, then like the case of Wolf-Rayet stars, the photosphere can be formed in the wind matter. And yeah, that's the case for Wolf-Rayet stars, for example. And that means that compared to the temperature of the hydrostatic core surface, actual photosphere of the progenitor, actual photosphere temperature can be much lower than the actual hydrostatic core surface temperature. And that can change dramatically the optical brightness. So here's an example. So a student of mine has made a CMF-Gen calculation of the spectra of 9 solar mass CO star progenitor. So there's a little amount of helium, but mostly CO composition. And what you can see here is that this dotted line is the black body spectrum according to the temperature of the hydrostatic surface core. And because this compact core is very hot, the black body is shifted towards the UV. But if this star has a very strong wind, for example, in this case, we assumed mass loss rate of about 2 times 10 to the minus 5 solar mass per year. Then compared to the hydrostatic stellar surface temperature, which is about 2 times 10 to the 5 Kelvin, the photosphere temperature can be as low as about 10 to the 5 Kelvin, so 2 times lower. So as a result of that, black body spectrum can shift like this, which is the dashed line. And this is the continuum spectrum. So the color strong, this purple line. And in addition to that, there's a strong emission lines here, you can see. So as a result of that, the V-band magnitude can be as high as -4 compared to the black body prediction of the hydrostatic surface core, which is about -1. So that means that if the progenitor has very strong wind, then optical brightness can be very high. So in that sense, strong wind, I mean, if the progenitor have very strong wind, then it would be easier to detect in the pre-supernova images.
And that event would be hydrogen-free, the one you're just showing, that model?
Yes,
okay.
All these are hydrogen-free models.
Okay,
yes.
Thank you.
Yeah. So, so this diagram shows you the prediction of the narrow V-band magnitude as a function of the surface core, surface temperature of the star. These are helium-rich model. And here we are, this black, these black symbols are our physical model with a physical mass loss rate. And this sky blue color is the prediction from the black body spectrum according to the stellar surface temperature. So the difference between the two gives you a hint how a stellar wind effect would affect the optical magnitude. And as you can see here, the helium poor models, the stellar wind effect can be very strong. So the volumetric, the optical magnitude can increase from here to here because of the wind effect. So this effect can be very important. For helium-rich stars, this effect is less strong. That's mostly because these stars do not have a strong wind usually because the mass is not very high. And also these stars are not as compact as helium-poor models. So the wind is not as dense as helium-poor models. And also we did some parameter study to see how this magnitude depends on the mass loss rate from the progenitor star. So the black symbols gives you the physical mass loss rate given in this paper. So that's according to the typical Wolf-Rayet star mass loss rate, basically. And this yellow color gives you 2 times higher, 5 times higher, and 10 times higher mass loss rate, and the 10 times lower mass loss rate here. So as you can see here, for helium deficient, helium poor models, if the mass loss rate becomes higher, then optical magnitude becomes higher very strongly. For helium star models, this effect is less strong. As I told you, this is mostly because mass loss rate here is not as strong as here. And then these stars also have fairly large radius. So the wind density is lower than in this case. But in any case, especially for helium-poor type 1c progenitor models, this optical brightness can sensitively depend on the mass loss rate. That's very interesting because from this, we can constrain the mass loss rate from the progenitor stars from the pre-supernova searches. For example, here we compared our model prediction with the detection limit in pre-supernova searches given by the group of smart smiths. So, for example, these dashed dot line give the detection limit of type 1c supernova progenitors in pre-supernova images. And dotted line is the detection limit for type 1b and c. So sort of in between 1b and 1c supernovae. And these are detection limits for type 1b supernovae. So none of these supernova progenitors were identified. So they only provided detection limits. But as you can see here, if the mass loss rate was strong enough compared to our physical mass loss rate, they would have been identified here. So from this, we can say that at least for these supernova progenitors, their mass loss rate were not really very high compared to our physical case. And another lesson we can learn from this here is that you need really very deep search to find out ordinary type 1b or 1c supernova progenitors. So in terms of the optical magnitude, you need at least -5. So it's very stringent constraint, of course, but anyway, you need really, really deep search. Otherwise, it would be very difficult to identify an ordinary type 1b or 1c progenitors. And IPTF 13BVN progenitors have been identified. So depending on the extinction correction, the optical magnitude can be either here or here. And this is the color diagram. Also, depending on the extinction correction, it can be here and here. So we found that they are marginally okay. So our physical model can marginally explain this the optical magnitude and color here. So it's fairly bright compared to most ordinary progenitor models, but it's marginally okay. So marginally within the error bar. Supernova 2017 EIN it's extremely bright. And also in terms of color, it's very blue. So our physical model cannot explain. And even with the extreme mass loss rate, it looks like very, very bright. And also compared to our models, it's too blue. And also we also compared 120 solar mass companion. Then even in this case, it's too blue. So, to me, it doesn't look like a progenitor star. So probably it was not the progenitor of the supernova, but it was something else to me.
But for this one, we could go back later after the supernova fades and see that it's gone. So has that been done, or maybe it's not able, you're not able to do that yet? That seems like a good prediction.
Yeah, someone has done it, but the data has not been published yet. So,
do you know what the answer is?
Yes, I don't know the answer yet. Yeah, a student of mine has looked at the data, but he could not tell because the data quality was not that good. So, but anyway, I would be very surprised that if this were disappeared. Yeah, it doesn't look like the progenitor. And 2019 YVR, this is another interesting case. And this is another extreme case because it's too red compared to ordinary progenitors. So it's another extreme in terms of color. Also, it's very luminous. So this one was type 1b supernova. And the progenitor candidate was very, very bright and very red. And if we compare our ordinary, for example, 5 solar mass helium star model, our physical model is here. So compared to our physical model, it's very bright. So to match this brightness, we had to increase the wind about 100 times. So if we increase the wind mass loss rate by about 100 times compared to the physical rate, then marginally can explain the brightness. But still the color looks too red compared to this model. So it's another outlier to me. But anyway, it can be a progenitor, of course. There might be other way to explain this color. For example, this supernova occurred in a very dusty environment. So depending on the dust correction, the color may be different and so on. So yeah, might be the progenitor.
So for that last one, I don't know if you're going to talk about it anymore, but there's also strong interaction seen in the light curve, like at 150 days or so,
yes,
which maybe indicates
right.
There's other things going on around the supernova, or maybe it had more eruptive mass loss rather than these more smooth winds that you're considering. Are those possibilities? What do you think of that?
That might be the possibility, of course, yes. But what I can tell you is that this is not ordinary progenitor. So it's not surprising that we could not find the really ordinary looking type 1b or 1c progenitors. We found only some outliers. That's because they are usually very faint in the optical band. So what we have learned from the pre-supernova results, such results, is that mass loss rate of most 1c progenitors would not be much higher than the physical value compared to the usual Wolf-Rayet star mass loss rate. And the IPTF 13 BVM progenitor looks marginally okay compared to our physical models. 2017 EIN is too blue and too bright. Maybe it was not the progenitor. And 2019 YVR, it was certainly an outlier as well. And you really need a deep search. The optical magnitude should be less than about -5 to find out an ordinary 1BC progenitors. So it would be very challenging. Okay, then I still have about 15 minutes. So maybe I'd like to address another topic. That means that another question I'd like to address is that are type 1C progenitors really helium deficient? That's another question interesting for stellar evolution aspect. Well, the classical scenario looks like this. For type 1b supernovae, you see helium lines in the spectrum. So yeah, it's very natural to assume that in the progenitor there was hydrogen, there was a helium-rich envelope. And for 1C progenitors, well, for 1C supernova, you don't see helium lines in the spectrum. So it's also natural to assume that the progenitor were helium deficient. But one problem, one complication with this idea is that helium lines are not really easy to make. That's because if you look at the photosphere temperature of type 1b or 1c supernova, it's about 7,000 Kelvin. It's not really high enough to make helium lines by thermal processes. But still you see strong helium lines in 1b supernovae. So you need non-thermal processes to make helium lines, and nickel can do it. So if nickel produced in the innermost layers by supernova explosion mixed out into helium-rich layers, then gamma rays produced by radioactive nickel can make some excitation of helium electron, and that they can make a good condition for helium line formation by non-thermal processes. So you need some amount of nickel mixing to see helium lines. But if the nickel is still constrained, I mean, if the nickel is restricted in the innermost layers, if there's no mixing between nickel and helium, then you do not see any helium lines in this case, except during the early times when the photosphere temperature is very high. So in this case, the supernova would look like 1C instead of 1B, even if the progenitor had helium-rich envelope. So I was wondering if we can test, I mean, if we can make some constraint on the nickel mixing in type 1b and 1c supernovae just by looking at the supernova light curves or supernova or photometric photometric properties of supernovae. So we made some supernova models assuming different nickel distribution like this. So this is the weakly mixed nickel and strongly mixed nickel here like this. So other conditions are the same. And I looked at how supernova light would become different. So this is the so-called kind of Kipling diagram for supernovae. So this is the x-axis gives you time since the explosion, and this is the mass coordinate. And this control line gives you the temperature in the ejecta of supernovae. And this is the photosphere defined by the Rosseland mean opacity. And as you can see here, so here the nickel is concentrated in this dashed region. So there is no strong nickel mixing in this model. But in this model, nickel is fully mixed in the entire ejector. And you see the difference in the temperature evolution here. The temperature goes down like this initially because of the expansion of the envelope, because of the expansion of the ejector. But here the temperature increases in this region because of the heating due to the radioactive nickel. I mean, heat diffusion comes here about 15 days later, the explosion. Because nickel is concentrated in the central region, it takes about 15 days for the heat from here diffuse out here. But in this case, nickel heating is everywhere. So the temperature evolution looks like quite monotonic in this case. So as a result of that, depending on the nickel mixing, the light curve looks very different. For example, if the nickel mixing is very weak, then you see here very sharp cooling emission here. But after that, because of the radioactive power, nickel heating, the main peak appears like this. And the color evolution looks like this. Initially, because of the expansion of the ejector, it becomes red. And after that, nickel heating becomes important at the photosphere, then it becomes blue again. But if the nickel mixing, as the nickel mixing becomes stronger and stronger, this initial bump disappears because initially the nickel is mixed out to the photosphere. Then nickel heating occurs very outermost layers. Then outermost layers becomes very hot from the beginning. As a result of that, the optical magnitudes becomes smaller. I mean, it doesn't become bright in the optical because they are too hot in the initial phase. And in terms of the color evolution, initially it's very hot. If the nickel mixing is very strong, then it becomes red. It becomes red monotonically as time goes on. So depending on the nickel mixing, the color evolution becomes very different. So I compared this color evolution for different type 1b and 1c supernovae. And for the case of IPTF 13BVN, as you can see here, initially there's the B minus V color becomes fairly red initially, then becomes blue and becomes red again. And this kind of shape is quite consistent with the weakly mixed model like this pink color here. On the other hand, supernova 2013 GE, which is of a kind of 1C supernovae, the color becomes monotonically redder as time goes on. And this is most consistent with a strongly mixed model like this. And for 2009 JF, you see initially it's pretty red, but becomes blue and becomes red again. And this is also consistent with weakly mixed model. And what I found here is that for most type 1b supernovae, they show signs of initial red and becomes blue and red again. For most type 1c supernovae, the color evolution looks mostly monotonic compared to this case. So this means that for type 1b supernovae, the progenitors must have helium-rich envelope, otherwise you do not see any helium lines. But the nickel mixing would not be very strong. I mean, the nickel must have mixed into the helium-rich layer, but the degree of mixing would not be very strong. So there must have been some weak mixing of nickel into helium-rich envelope, but the nickel mixing would not be very extreme. For type 1c supernovae, to explain the color evolution like this, you need very strong nickel mixing. And that means that given that these supernova do not have strong helium lines, they must not have any helium in the envelope. As otherwise you must have seen strong helium lines, because nickel mix must be very strong in this case. So, so I think then the color evolution can give you very strong constraint about the nickel distribution in the supernova ejecta in this way. And also in this way, you can infer whether progenitor had helium-rich envelope or not. And another interesting finding made by a student of mine is that it seems that there is also systematic color difference between 1B and 1C supernovae. So she collected 18 1B and 18 1C supernovae, and then she made a B minus V color distribution at the V band peak. And it seems that 1B is systematically bluer than 1C. And we tried to model that, then to explain the difference between the two. So she made hundreds of supernova models using helium-rich models and helium-poor models. So this blue color gives you the result of helium-rich model, and red color gives you the result of helium-poor model, and for different degrees of nickel mixing. So small value means that weak nickel mixing, and larger value means that stronger nickel mixing. And as you can see here is that supernova model also predicts that helium-rich models are systematically bluer than helium-poor models. And the reason for this is because of the composition difference mainly. And as a result of that, there is also difference in the opacity in the ejector. This is the helium-rich model in this Kipnan diagram. And dashed line is the nickel concentrated region. And this dashed line gives you the V band peak moment. And this, black line is the evolution of the photosphere in the ejector. And as you can see here, photosphere recedes into the innermost layers as time goes on. And compared to the helium-poor models, and this is the helium-rich model and helium-poor model, the helium-poor model, photosphere remains in the outer layers compared to the helium-rich models. And as a result of that, photosphere temperature remains cooler in this case than in this case. And that's because, just simply because helium-poor models have higher opacity in the ejecta in the outermost layers. And that's the reason why the photosphere remains in the outer layers. And this can explain this systematic difference of, This may explain this systematic color difference at the V band peak. So this can give you another evidence that type 1B and type 1C progenitors have systematically different chemical structure. So type 1B supernova, they are indeed helium-rich. And type 1C supernovae, their progenitors seems to be really indeed helium-poor. Otherwise, it would be difficult to do this, to explain this systematic difference of colors. So, what I learned from supernova light curves and color evolution of type 1BC supernovae is that color evolution can provide a clue on the nickel mixing in the supernova ejecta. And also it seems that type 1B and 1C ejecta, the nickel distribution seems to be systematically different. specifically the nickel seems to be more widely mixed in 1C supernova ejecta than in 1B supernova ejecta. And also 1C supernovae seems to be systematically redder than 1B. And from these two, I could conclude that 1B progenitors are distinct in chemical composition from 1C. So there must be some dichotomy nature in 1B and 1C progenitors. 1B progenitors are indeed helium rich, and 1C progenitors are indeed helium poor. And this confirms the conclusions of many other observational studies like these people. So then the question is that how to remove helium envelope. Well, why this is problematic is because in terms of the ejecta mass, 1B and 1C, they do not show much difference. So the ejecta message looks similar. So that means that 1B progenitors and 1C progenitors, they seems to have similar final message. But stellar evolution models always predict that 1C progenitors are much more massive systematically than 1B progenitors at the very final stage. So having the similar final message and remove helium envelope in that way seems to be very difficult for me. So in the future work, I need to figure out how this can happen in the nature. So I stop here. Thank you for listening. So.
Okay, thank you very much, Sung-Chul. So I think we can take some questions. Yeah, and Tony has a question. You can raise your hand also in there.
So just
you don't
like
have to, Tony.
If you had more time, you may have gotten into this, but there's you know, if the helium is being removed in cases where there's stronger winds, I mean, that suggests maybe a metallicity connection, which then would suggest for galaxies, you know, either more metal-rich galaxies, more metal-rich environments, there should be a connection there. But 1C is typically, I thought, maybe I'm taking 1C broad lines, but typically they happen in sort of dwarfier galaxies. So I don't know if you can just comment on whether you expect any galaxy, you know, type connection between 1Bs, 1Cs, or what should be done there.
Yeah, that's a important point. Indeed, metallicity effect would be very important in this case. So I know that some people looked into the host galaxy metallicity difference between 1B and 1C, but data is not really good enough to make a strong conclusion. But yeah, certainly 1C progenitor seems to, I mean, 1C seems to occur preferentially in higher metallicity region. There's another question by Joshi Simon in the chatting. 0.6 magnitude difference of dust reddening should also make the star appear significantly fainter than its true magnitude. So in this scenario, it would actually be brighter than the model.
I think this was related to the supernova 2019 YVR. Maybe.
Yeah, that's right. Yeah. Here in this diagram, we made a correction for dust extinction. So, but even after the reddening correction, there seems to be a systematic difference. Yeah.
I have a question also, Sung-Chul, about actually similar to what Josh was mentioning. So many of the binary strip stars, when they explode, they are expected to explode during mass transfer, and or at least they still have a companion star. So in your models for like the color of the pre-supernova image, does the companion star matter? And do you think that there should be a difference in like the supernova because of the companion, basically.
Yes. I do not have figure that now, but here the open cross gives you the color temperature relation, I mean magnitude temperature relation for O or B type stars for jumps and evolved case. And composite spectrum also we made. We also made composite spectrum, and it can make some difference, especially if the companion star has very high mass. But if the companion star mass is less than about 20 solar masses, it doesn't make really big difference.
Okay, thank you. And the fact that the star would explode during mass transfer, does that matter for the supernova?
Yeah, no, during mass transfer, well, so for some case, BB case, yeah, it can explode during mass transfer. But in terms of supernova like ours, it would not make a very big difference, I think, unless mass transfer rate is extremely high. So if the mass transfer rate is, for example, 10 to the minus 3 solar mass per year, 10 to the minus 2 solar mass per year, then probably the circumstellar matter would be very, very large, and it might make some difference, yeah, during the early time.
Interesting.
Yeah.
Do we have any other questions or any last bits here? Okay. Then I think that I will stop the recording.